Okay. So okay, we have some libraries to be included in your project. This is the VFDB library. Okay, you must be install the VFDB library to get the information from the what from datasets. Okay, and this datasets presents this application generates this libraries. Okay, and so in VFDB dataset or the database, we have such kind of information or the files, which means that this dot file includes your ECG files. Okay, these attribute files includes the annotation for specific ECG values. For example, in the ECG we have three kind of signal: P, QRS, and T. Okay, contraction represented with the QRS signal, and repolarization represented by the T wave signal. And in biomedical engineering, there could be a meaningful pattern for the diagnosing of some abnormalities in your cardiovascular health conditions. Okay, that's all. And so you must be install it, and you can search the internet on this term, and you will find some basic example about it. Okay, and we also include the NumPy SMP, and also we need to matplotlib.pyplot in order to visualize the whole data in here. Okay, and so if we have this dataset or include your 100 attribute and dot file and header file, we can obtain the record values with the VFDB dot rd records, the specific name 100. This is the name of the R database function or this file. Okay, and we can also give to SAMP2 to region of your ECG signal. For example, 0 to 15,000 value is included to this record. Okay, and also we can give the annotation file in here, vfdb.rd annotation, and 100. This is the type of the attributes, and SAMP2 15. Okay, these are general collection of the ECG signal and its annotation. Okay, this annotation must be used to for your training set or the Y value, output value, because we want to find out this annotation by using our proposed neural network or the convolutional neural network, right? This record is a simple dictionary values and includes the whole such kind of information. For example, the patient name, the patient record, sampling frequency, or the data, or the condition of the cardiovascular case, and blah blah blah. You can easily search this record to to take the key values of dictionary type. Okay, so in order to obtain the record, we can use the P signal function. Okay, this is our representation of the ECG values in the voltage terms. Okay, and so this returns to the R array related to ECGs. Okay, and so we have the two channel value in here, like this one, data 0 and 1. Okay, there are two records for the same patients in here. This records represents the different channel of the obtaining the ECG values. In ECG, in simple case, we have three channels. One channel one channel and one channel. And so we can obtain the whole electromagnetic field or the electrical currents from the what? From some electronic device, which call it the ECG circuit. Okay? And so this channel represents to the what? For example, Eindhoven 1 channel and the other Eindhoven 3 channel. In biomedical literature, we can call it, but you may not use or you may not know this information. Just focus on the data, okay? So, we can create the times values in here like this one, MP arrange function with the len of channel 1, okay? And the type float should be given in here, and also record fs must be given in here because we have the specific sampling rate in here like this one, and so this sampling rate should be divided by this term in order to get the true time values, okay? Because we have the 15,000 data points in here, and if we divide by sampling rate, and then we will get the time values, okay? So PLT figure fixed size is assigned with the 12.6, okay, and PLT subplot to 1 and 1, and PLT plot times and channel 1, and is the color, for example, B, okay, and PLT X label times sec, and PLT Y label amplitude voltage, okay, and PLT title ECG channel 1, okay. The other term is the same structure, but the channel 2 and channel 2, okay. Rest of the code is the same, but this must be J, okay. And tight layout should be given, and PLT show must be written on this page, okay. And so if I run this code, and then we will get the what ECG channel or ECG values from the what, from some patients, right? And so these greater values represents the what, the QRS signal, okay? And this terms is the what in the other section. This is the QRS signal, and we will find out this pattern from your neural network, okay? And this is the T wave signal, and this is P signal, this is QRS signal, okay? And so in your heart or cardiovascular system, if this signal occurs and then we contract the whole the hearts, we will know that. And if we have this pattern like this one in here in this channel, and so we have the what, the repolarization or the relaxation of your heart, okay? But in each channel we have different characteristics, okay? And so if we have the many channel from the patients, and so our neural network what this will show the best performance if the number of input vector increases in this case, right? Okay. And so what? No, the channel 1 and channel 2 represents the electrical activation of your heart or the cardiovascular system, but the measurement techniques are different, and so we have two different vectors with the same information. But in math we enrich our data representation to find out what the contraction of your heart, okay? But if we can use the Fourier transform or the Fourier series, and then we can generate more pattern or more meaningful pattern, right? Okay. Yes, yes. and yes. Okay. And so for the Fourier transform we can use another function in here like this one, where 2 ECG fs dot pi. And so this ECG can be represented by using the Fourier series. Okay? Okay. And so this code is the same with this one. Okay? But ECG 1 and ECG 2, this is the basic representation, so obtaining the our data in here. Okay? And after that we should create the times pattern MP arrange function in here, the len ECG1 and D type float divided by record fs, right? It's the R generation. And so fs frequency, sampling frequency. Okay, sampling frequency. This records is a dictionary with some specific key values. Okay, and so if we call the fs, and so this records this is the sampling frequency values of this record. Okay, so in order to calculate the Fourier transform, we can take the Watt Fourier coefficients in here, like this one. For example, where is my code? Is my code? Okay. This code, copy right now. Okay? Because we can copy of whole of this code. This code is not different from the others. Okay? Function definition. And we need to reconstruct the R signal also in here, and I can get this term like this one, copy all of these things, right? Okay. And so this is so simple when it have this kind of codes. I can apply this code to the any case. In this case, ECG. Maybe you can use the EMG value. Maybe a picture, right? And so the main code can be given here. This one. And the num terms can be assigned to 10, and coefficients can be assigned with the Fourier coefficients function with the times parameter ECG1 and num terms, right? And after that the reconstructed signal can be given with what the individual terms like this one, and reconstruct signal function can be called with what the times and coefficients, right? And you can draw the PLT figure, fixed size 12.8, and PLT subplot can be given 311, and PLT plot times and ECG1, and label ECG1, PLT title original signal, and PLT X label time, Y label amplitude, and PLT legend can be shown in this case. In the second case, we can create the PLT subplot 312, and for n term in enumerate with what the individual terms, like this one. And so PLT plot with the what the times, term, and label to what f term n plus 1. Okay, and the other terms are same, individual signals in here, legend, and after that should give the what reconstructed signal, right? Reconstructed signal, reconstructed R ECG. Okay, and so this title is the reconstructed signal, time, amplitude, and in the final case PLT tight layout, PLT show must be given. Okay, and so if I run this code, and then we will have this information, right? In the 10 terms we get this amplitude, this signal like this one, but the true signal is in the what, in the first figure, right? Okay, but how about this? I can explain in here like this one, but in this term we cannot model this parameter because this signal is not the same with the first one, right? But if I increase the num terms in here like this one, and so this signal is also the first or the improper form, right? Because we have the 4000 data, or the 440 seconds value should be represented in the one form. Okay, if this is the heart rate or the ECG is in the periodical form, and then we should only utilize to the what, to the this term up to this one, because if the cardiovascular signal is in the period, and then we may only contain this one period signal. In the Fourier series, if we have the more data to represent the sinus and cosinus function, we may have the what the true conditions or the true representation. But in each periodical signal, we can apply it, and then we will get the more understandable form in here, like this one. But num terms is increased in here, like this one, and then voila. See that? Okay. And this is one signal. This is one signal, but we have the 100 different data to create your pattern. This huge advantage, right? In mathematical operation or in the theory, if we have the more length signal or the tall signal, like the 15,000th value, is hard to represent with the Fourier series notation. Okay, because we have the many components to represent the sinus and cosinus. Okay, but if you have the periodical signal like the ECG, because in each heartbeat we have the periodical signal with the same pattern, and so if we model the one beat, and then we can model the every beat. Yes, because the Fourier series can model one period, not the whole of this period. Okay? Do you understand this notion? And so you can apply the any signal, any form to this representation, because we have the 1000 different data in here, and the same signal is obtained by using these terms, right? With some error, but less error. Okay, it's not identical in this case. Okay, this is the what? This is the Fourier series application. But we have also Fourier transform to be applied on this code, right? You can apply the Fourier transform as well in here. And so you can create the word tree ECG FT dot pi. Okay, and this is the not pi t, pi. Okay, and so in the first case we should give the what, the same code can be given in here like this one, right? It's the 1 bit. Okay, and so what about the function definition? In the function definition we have the, where's the code? It's the fs. Okay. We have these codes to be what? To be used in this notation, right? We can use it. We own it. Okay, and so the main code can also be given in here. Like this one. So okay, get this code, and then we can plot the figure with the what, the fixed size of the what, 12.8, right? And PLT subplot 211 and plot time series with the ECG1 times and times series data in here, and PLT subplot 212 and plot discrete Fourier transform with what, ECG1 sampling frequency values, which is equal to the what, record fs, right? And also the FT coefficients, right? PLT tight layout and PLT show can be given in this case. So this is what, this is the basic representation of what, the Fourier transform in ECG domain. Okay, and so this is what our frequency representation of our code, which means that we have the what, the sum sinus and cosinus to create this pattern, but the main components is up to what, the 50 Hertz, right? Right? Okay. How about the distance? In the previous lesson, I talked about the what, the Fourier transform can compress your information to the meaningful data. In Fourier series, we can increase, but in Fourier transform, we can decrease, compose the whole data into the one form. Okay, and so this can be increased right now, like this one, right? I can do that because if we have used the more data in here with the 15 times, and so we may have the more information from this time, because in each beat data compressed into the frequency characteristic, and so this is more accurate representation of the what of our signals. Yes. Yeah, so we don't know that, because but in the inspection of these codes, I can say that these codes like this one, we have the some bias value. This indicates some bias value at the 0 frequency, right? This is the bias value. But we have the meaningful components in here, for example 2 Hertz and 3 Hertz and 5 Hertz, right? And the other terms may be noise, but we don't know, okay? Because if you're, for example, the measurement may increase your noise values in here, but in the inspection of this graph, I can say that the 2 Hertz is meaningful, and 5 Hertz may be meaningful, and the 6 or 7 Hertz may be meaningful, right? But we don't know it. But if you have this pattern, and so you can apply the whole data into your neural network, feed the whole neural network, maybe your neural network can solve this problem right now. Even if you don't know the mechanism, or even if you don't know what is whatever the noise is included or not in this case. Yes. You can enrich the whole pictures with the by using this code, and then you can feed as an input data, and you may learn some kernels anyway, okay? This is the pre-processing phase, your data. But if you have the one picture for your convolutional neural network, or you may use the 10 pictures with the Fourier transform, Fourier series, and something like that, okay? And so if you have the more data to represent any function or any output, and then you may utilize the advantage of these codes, okay? So, any question? Okay. In the Fourier series, one data split into 1,000 different data. In the Fourier transform, 1,000 data compressed to the 1 or 2 meaningful data. Okay? Okay? Mm-hmm. Yes, in the Fourier transform, we can. Yes, in the series, we can collect the whole or some whole of these components in order to what? In order to create this pattern. For example, we have this signal. We construct signal, but this is one data, but this is 1,000 data. You may feed your neural network by using this data. This is the proof of the whole collection. This collection is summed, and resulting signal is your ECG. This is the proof. Okay? Just proof. Okay. Okay. I'm continuing. Okay. What about the wavelet transform? Have you heard about the Wavelet transform? Nothing? Just kidding, right? Your signal and system lesson. Okay. And so, in the Fourier transform, FT has some disadvantages. Like, for example, what the temporal information cannot be included. Absency. Temporal information, okay? And it's entirely depending on the what? On one basis function. Basis function means that convolution function. But in the CNN application, we can define the 10 different kernel with the learnable parameters. These are the disadvantage of these things. But what about the temporal information? Temporal information means that in Fourier transform, so long, and I can change this data. I can't wait for this code. Okay, and so in this code we obtain the whole 1 second period signal as a one term in here, but we don't know the instantaneous frequency of this term because it's equal to the, for example, to what the 70 Hertz maybe happen in here, but in this case maybe 2 Hertz, 2 Hertz, 2 Hertz, 2 Hertz, 2 Hertz, maybe it's the 5 Hertz, 10 Hertz, because it's speeded up in this case. But in this case we have the some characteristics instantaneous frequency. It's highly dramatically increased, right? You can see that, right? Everyone see? You can see? You understand what I'm saying in here? Okay. Yes. Hocam gördük yani. Ne soruyorsun? No. It's okay. And so, in this definition, in simple case, I think we need to create some xt signal in here, like this one, xt, the parameters of t. And we suppose that we have this kind of information in here. Like this one. Okay. And so, how can we obtain the temporal information from this space? In a normal case, we can take the some window pattern in here, like this one. Window length can be determined from this signal, and in each case, we can take the some signal in here, like this one, as a section in here, section 1, section 2, and section 3, and section 4. And so, we can apply the fast Fourier transform in here, Fourier transform, and then we will obtain, for example, f and t, like this one. These terms creates maybe these things. These terms maybe creates the what? These terms, right? F and t, because we have some greater frequency in here, right? You see that? Okay. And so these terms f and t may be given like this one, and the other term maybe generates to the f and t like this one. Okay, and so in each pattern we can create a distinct window, and then we can create some distinct patterns for a given window. This is called the short time Fourier transform. Short time Fourier transform. This is the highly efficient technique, but we should utilize the window-based searching algorithm. Okay? This is the problem for the short time Fourier transform. This is represented with the what? With the uncertainty principle in nature, which means that if we have some ball with the speed values in here like this one, we have the general speed and the position in here like this one, we have x, and if we are using in here the uncertainty principle means that if we increase the position of this term like this one, and so we can precisely measure the velocity values. Okay, this is certain, but highly certain. But the position have greater range. Do you know Heisenberg? Breaking Bad. Okay, and it's Breaking Bad. Its code name is the Heisenberg. Heisenberg found the what? Uncertainty principle. If you are measured any particle in the universe, either speed or the position is accurate. In both cases cannot be satisfied. Okay. And also, if you want to measure the precise position, and so we need to decrease the precision values of the speed. Okay. And then what? This principle is the same with the what? Frequency and time in the signal pattern. Frequency and time. Okay. And so we have specific time and specific feature, because we need to get the instantaneous frequency at the instantaneous time, right? Okay. So we have some pattern here, and then what? If we increase the time pattern or decrease the sensitivity of these values, and so we can create the highly accurate measurement in the frequency domain. But if we take the frequency range in here like this one, if we increase these values, and so we can highly sensitive time measurement can be applied in this case. And so what is wavelet transform? Wavelet transform means that wavelet arrange or change this pattern at the instantaneous time, and so we can get the instantaneous frequency from the signal to change this pattern coming from the what? Uncertainty principle. Okay? Do you get the notion or the idea? Okay? I will show that. I have every answer. So funny. Okay. And so in the graphical representation, we can represent the short time Fourier transform f and t like this one. This is the window values. Each of the box represents the window. Okay? And so we can create the window in here, window, but we can search this box at the at same equal space. For example, this is the 50 Hertz, this is the 20 Hertz, and then this space does not narrow or expand. But in the wavelet transform, we can generate this kind of pattern, like this one, T and F. And so, for example, in the first place, we can split the time to frequency like this one. But in the second case, we can divide our range like this one. In the third place, we can divide whole the range like this one. at each time divided by 2, we can generate the more frequency pattern. In the last case, for example, we have the many detailed region. Okay? This is the level 0, this is level 1, level 2, and level 3. And what about this code? This code represents, or this representation means that if we want to get the highest frequency, which layer should be included or examined? L? Okay, you get to hold the picture right now. And so, this is wavelet, this is short-time Fourier transform. What about the Fourier transform? Fourier transform like this one. One box. This is the window based, this is the wavelet. Okay? And so, how can we create this pattern? This pattern can be supplied or satisfied with this formula. X omega n times xt. This simple convolutional operation. But the omega n is represented what? This form, like this one. We can create the many levels, many convolutions, and then we can generate the what? The 0, 1, 2, 3, 4 different signals by using the wavelets. Right? Okay. Okay. The last code is totally given about what the wavelet transform. Therefore, wavelet ECG wavelet dot pi. Okay. So, as always we do, we can copy off this code like this one. Okay. This is ECG1 and ECG2, and after that we need to include the what? Import pi wavelet. This is the standard library to what? To obtain the each level of the wavelet from the ECG signal or any other signal. Okay, you can utilize this function formula. Okay. So, one of the wavelet type is the Dawbeck 4. It's the code name DB4. Okay, and we can give the level 6, which means that this frequency pattern split into the what? The 6 frequency range. For example, if we have the sampling frequency is the what? 360 or 500. In the first level, we have 500 to 250, and in the second level 250 to divide by 2, 125. Okay, which means that in the first level 500 to 50, and in the second level we have this frequency components, and in the third level we have this components, and goes on. Okay, we can split the frequency range by using this level representation. Okay, and so signal length can be defined in here like this one, len ECG 1. Okay, and so coef 1 is equal to the what? The pi wavelet dot wave decoder can be called with what? ECG1, and wavelet type and level should be equalized to the level. Okay, and coef 2 is also given in here like this one. Okay, this coef includes what? The frequency components of your levels, and so the time values can be created with what? The MP linspace, like this one, 0 to signal length and len coef and endpoint false or coef in coefs. Because we have the some list data but the two-dimensional list data, and so in each data we should create the time values. Level 1, level 2, level 3, level 4, level 5, okay? And also times real ECG can be given with the MP arrange with the what, the len ECG1 and D type float. But in this case I cannot divide it by the record because I need to show the sample times in here, but I can do that. Divide by the record fs can be utilized in here, but we don't need that coefficients. And so visualize the wavelet coefficient at this one, PLT figure fig size 12.6, okay, and PLT subplot is in here 211 and PLT plot times real ECG with the ECG1, and label should be assigned with what, the real ECG1, okay. And after that we should give I and coef in enumerate what, coefs 1, okay, and plot PLT plot times values for the specific indice and coef plus I times 2. I times 2 is not necessary in this code, but if I don't put this code, each signal is shown at the what, at the same level, okay. 1, 2, 3, 4 creates the what, the different patterns in normal case, okay. And the label in the graph I will explain this utilization. Level I, okay. And after that time values, okay. After that PLT title, the wavelet coefficients ECG1, okay. And so in the second case I shall only change with what, 2, okay, and this is 2 and this is 2 and this is 2, and PLT legend must be given, and PLT tight layout and PLT show must be given at this case. Okay, we have this pattern in here like this one. This I2 value is carry this signal into the upper one, okay, just like that. If I remove this code in the second place, each signal is on the same plane, okay. Do you understand this code? Okay. And so if I rerun this code and we have the ECG signal in the blue lines like this one, and so in each components 1, 2, 3, 4, 5, 6 and 7 can be summed and created to the what, to this ECG signal, right? Yes, yes. All the wavelet coefficients can be collected, summed, in order to what? In order to create the real ECG signal. Okay? But in the instantaneous frequency characteristics, like this one, just look at this pattern in here. Firstly, this is the QRS signal in here. But in the QRS signal, we have some deviation in here with the higher components. And so we can easily restore. We can easily take this pattern into examine this code like this one, because in this case we had some peak value. Bakın, look, this is the peak values. The pink signal represents the QRS signal in here, right? We can easily analyze that. We can cache that by using this transform. Okay? This is the advantage of the wavelet transform to obtain the instantaneous characteristics.
The other one looks like shows its relevance.
Maybe, but just suppose that if I want to use the ECG signal to train your CNN or the neural network, there could be some problems. But in these signals, there's no problems, because the identification is seen right now, right? We don't see this frequency characteristics, but if we apply the wavelet transform, and we can generate these patterns. Just like this one, this is the wavelet transform pattern, and so if we have a specific operator or convolutional operator for each layer, L0, L1, L2, L3, we can generate these patterns. For example, the hard filter, Dobek filter, is applied to level 0, and then we get this orange level. Okay? This is one filter results. And the two filter level 1 is some narrower pattern is convolved with this signal and generate this green level, right? Right? You get it? And after that, we narrower convolutional pattern, narrower matrix is applied on this signal, and then red signal is generated, and goes on. Okay. And so we can create the 20 level in here. Yes. This error case. But why? Why? Yes. Sampling frequency. If we divide by 20, and so 32 values is divided by 20. 2 over 20 times divided this frequency level. Because at each case, we divide by 2, 2, and 2. Which means that 2 over 20 parts. Yes. But the wavelet transform is always correct in here. In this case, even in this case, if we can hold the signals, we obtain the ECG value. But this is not a meaningful data.
If we get the neural networks data, it is meaningful. Maybe, but you must optimize this pattern also. How many levels should be used in this code or in your code? Maybe it's more informational, and so level 1, level 4, and level 6 are the best way to train your neural network. You need to choose that by the inspection of this code, right?
So you cannot see that code. But in the first component, for example, if we have the tree level, if they have the tree level, and we have the sampling frequency, for example, 306, and this is the true representation of our code, because we have the record fs is equal to 360 hertz and 90 and 90 and 45 and 45 to 0. This case 360 to 180 represents the L3. Yes, L3. And 180 to 90 L2. 90 to 45 L1. 45 to 0 is the expanded, the more expanded region, 25 to 0, because it's the slowest frequency at this case. Okay? You get it? But it's no. So I get it, but it's a more mathematical information about this code, and I can only show that this term like this one. Okay. You cannot decide that, because it's in your case maybe 20, but maybe 3. But in the ECG application, for example, in the ECG application, I know that the meaningful signal is in the range of the 0 to 100 hertz. The upper values of this code is unnecessary information for the physiological information. In your case, maybe it's up to 200 hertz or 50 hertz. I cannot guarantee. You should also you should always try and catch the patterns. There is no exact answer for this question. You must try it. But in the inspection of this code, for example, we have the tree level in here, like this one, and so this QRS pattern, in this case, in the tree level, we can catch the whole QRS pattern with respect to the 5 level, and so we can use the 3 level. Okay? Right? Yes. I cannot say that this is true or not, because in the signal processing and in the neural networks, I cannot say that this is it. You need to optimize it, everything. Yes. It's called the hyperparameterization in the pre-processing stage. It's with respect to your performance in the neural network application. Okay, this is called the hyperparameterization. In your project, you will accomplish the hyperparameter optimization. Okay. So, how can you use the wavelet coefficients? You can create the generalized pattern for this code. For example, we have the application level, the last code is creating the data set as an image. I will prepare this lesson also in here, like this one, like the CNN layer. We can show the wavelet, different wavelets in here, like this one, Bayer 1.1, Bayer 1.3, and the other terms, or the whole kind of wavelet list can be utilized in your code. Okay? But if you choose this pattern, and so the ECG dataset can be created in here. But with a simple example, we have the ECG signal is a one-dimensional data, we can convert each level, 5 level wavelets with the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 times 5 is equal to 55, and 55 we have at the one term 56 values can be seen on this page, like this one. We can convert or create the one signal to the image, like this one. See? This is the representation of the R signal in a Windows base to the watt to R frequency pattern. I can generate this image from the one-dimensional data, like this one. Okay? It's more meaningful. If we choose the whole kind of wavelets, like this one, we have the 100 different information, like this one. Okay? Oh, 600 different information with the level 5. We have the 100 different type of wavelets, and the 5 level is included in here, and so we have the 600 different data from one signal. No. So this is my case. This is my case. You can utilize the Fourier transform, or you can utilize the Fourier series to enrich your data. But in your application, for your application, maybe Fourier transform is the best candidate to train your neural network. You cannot know that. Please learn about that. I cannot say this is true or not. Please. Okay? Okay? Okay.